having defined what a limit is mathematically, let's try to see why we actually need it. I mean, if you think about it, for most functions, the limit is just the value of the function at that point. So why should we care? And the answer, well, is that limits allow you actually to estimate the value the function is getting to, even if it's not defined. So it's really useful. And on top of that, limits will be crucial to define these incredibly small quantities, very close to zero but not zero, that are actually part of a definition of what a derivative is. So let's try an example. You can also find this in section 3.3 in your lecture notes. And we're thinking about something very simple, but just so we can understand what we're looking at if you've never covered limits. If you have, then this might be a good recap, but you're also free to look at more advanced problems. So the function we're going to have a look at is f of x. So let's say that you want to calculate the value of this function at x equals 1. So what you do is you'd plug in the values there, right? You get 1 minus 1 over 1 minus 1, and you get 0 over 0. Now the problem with this is not a number, it is undefined. What this actually means is that the function is not defined when x equals 1. So as you will see, this is a point of discontinuity in this function. But the limit actually exists. And a way that you can do this is with your own calculator. You can have a look at f of x when x tends to 1 from negative values, and f of x when x tends to 1 from positive values higher than 1. So what you'll see is that as you plug in values, this will tend to 2, and the same thing goes here. So numerically, and I'll leave it up to you, you can explore tools like Wolfram Alpha. So numerically what we see is that from the left and the right, the function approaches 2. At x equals 1 exactly, it is not defined, but the limit actually, when x goes to 1 of f of x is 2. Now, solving limits numerically might be useful, but it's not very elegant. It requires you to have a calculator, plugging in a lot of values, and making the assumption that this actually goes to 2. Because it keeps getting closer and closer and closer, but it never really gets to 2. So there is obviously a more elegant way of solving this limit specifically, and also elegant ways to solve virtually any limit. It's just that some of them take a little bit more practice, intuition, and time. So let's try to do this in a more elegant way. Now, to solve this in a more elegant way, what we can try to do is to re-express part of this into something that we can then cancel out. And in this case, we're going to look at the top part, and you can see it in the lecture notes as well. This is the first example, and then we're actually going to systematically list different things you can try to solve limits like this. So in this case, what you can do is to write x squared minus 1 over x minus 1 as x minus 1, x plus 1 over x minus 1. And it is important to understand that you will be able to cancel this because x minus 1 will be different from 0. That is because we're taking the limit, we're not really replacing it. So if we do this, then the limit when x tends to 1 of f of x, that's x squared minus 1, x minus 1 will be equal to the limit when x tends to 1 of x plus 1 over x minus 1. And the great thing is that you can actually cancel these terms and end up with the limit when x goes to 1 of x plus 1, which you can very easily solve, because in this case you can plug it in and you get 1 plus 1, which is 2. So this is a simple case where if you re-express your original limit, you can cancel out a term. You can check that mathematically you can do it. You cannot do it if this equals 0. Great thing about limits is you're going to that value, but it never really gets there. So this is applicable once you remove that part that is going to 0 at the bottom. You can then sub in. This gives you 2. But note that in the next videos and sections, we'll actually look at a list of things that you can do systematically to solve any limit. And one of the important notes already, I'll come back to this, is that whenever you're trying to solve a limit, you should always first try to sub it in. And in many cases, for most functions, you will get the limit straight away. In this case, this is not happening, and then you can try a series of methods to actually nail it down.